So we have to discuss about BFS, DFS.
BFS and DFS, sir.
BFS and DFS, is it? Okay.
Yes, yes.
Okay. Apart from that, everything was discussed? Or?
Yes, everything is discussed.
Like DAG, topological sorting and everything, is it?
No, sir.
No, not DAG.
So not DAG and not topological.
Okay.
No, sir. No, sir.
Okay. Okay, let's do one thing. अभी तक कहाँ तक discuss हुआ है? We will do some problems of from activity, or if you have any doubts in activity, we will do those first. And then we will, at the end of this session, I will take up this BFS and DFS and DAGs and topological sorting. Okay.
Sir.
Okay, or shall we do?
Cyclic graph.
Sir, till vertex covered.
We can directly start from BFS and DFS because there
Yes,
is
sir.
a lot of topics. Like
Yes, sir. Yes, sir.
So the main doubt is in DFS. Like
Like
DFS is
forward-
quite easy compared to DFS.
Forward is, back is, something like that.
Okay, okay, okay. So let me just share my screen now. So will others join, or this is what the crowd is like? 30, I can see 30 people.
No, other will come. Actually, English is going on, sir. Like,
Achha, English is still going on.
they, I think they, yes, they are going on.
Okay, is my screen visible?
Yes, sir. Yes, sir.
Yes, sir.
So basically, how is graph theory? Matlab, are you guys liking the topic, or?
Yes, it is
Yes,
very
sir.
interesting. Very interesting.
Interesting, sir. Better than limits.
Better than limits.
So is this week for graph theory easy, or is it just deceiving in some sense?
What do you mean by deceiving?
So like looks easy, but when we dive into the questions,
Is it? Are you facing any problem while solving the problem?
No.
No, right? I feel, matlab,
these are just algorithm, no, sir?
yeah. Even I feel like the most enjoyable part in Max 1 is from week 10.
yes, sir.
Yes, sir.
So when you solve problems, or when you
This
see
graph thing is completely new and very interesting.
yeah, it excites you to watch one more lecture after one more.
Yes, sir.
Yes.
Yes, sir.
For me,
No, actually,
personally,
he's
it
teaching
actually
also.
excites.
Actually, it has a practical example, no? So
Yes.
that's why.
Sir, your voice is a little bit low, means I am not able to hear.
See, I am shouting now, and I have to shout for continuously. So what I suggest is, those who have headphones or earphones, I suggest you to have that, because
Sir, your
I
voice is
can't
clear.
wear them, sir.
okay,
I can't wear them. Some medical issue is there, that's why I can't wear them.
Okay, I will try to shout, or at least some speed.
No, don't shout. Just okay, means.
Okay. See,
I
I will
just-
try my level best. Okay.
Sir,
Okay,
voice is quite good, I think.
Okay. See, those who are in with earphones and headphones, I think for them it is very clear. Those who
Yes,
doesn't
sir.
have those things, maybe I will be little louder. Okay, I will increase my voice. Okay, let's do few things first, and later we will discuss few problems. Let us start with BFS and DFS. Okay.
So before that, can I ask something?
Yeah.
Yeah, sir. What are in vertex and out vertex, sir?
Inward vertex and outward vertex, is it?
Is it anywhere anyhow related to in degree and out degree?
Yeah. See, in degree and out degree are the terms we use for a directed graph. So if
Yes,
I have
sir.
any directed graph, let me say like this. From C and D. Okay, this is a directed graph. Is this
Yes.
a directed graph?
Yes, sir.
Yes.
Why?
Because it has direction, it has
Directions,
arrows.
the edges of direction.
Like A to B.
How to? Yeah, we can determine how to vertices are connected. So
Yes.
So you look at you can actually, by looking at the graph itself, you can identify whether it is directed or undirected. So undirected graph is basically which has each and every edge has both the directions. So like this, you see A and F has an edge which goes both directions, correct? So from F to A there is an edge, and from A to F also there is an edge. You can traverse. So this particular direction shows you in which way you can travel among these vertices. So you can only, if you see this particular edge here, it shows a direction from A to B. So that means if you do any algorithm, if you perform any algorithm, or if you see this particular graph, these graphs are coming from a relation. So here what it says is this particular edge says A is related to B, but not B related to A. So somehow you can only travel from A to B, but you cannot come back from B to A. So that is what this particular edge shows you. There is a direction for each edge.
Sir,
If that particular
Sir,
direction is, yeah.
But sir, like as you said, A to F, this to have the both direction. So if in one graph we have directed like only one direction and both direction together, then what should we call them?
See, this is a directed graph. See, when will that become undirected is every edge in your graph has both directions. So
Okay.
this AF edge, you can see the AF edge, right?
Yeah.
Like this, every edge in your graph should be bidirectional. Then that
Okay.
particular graph, we don't give the directions to the graph, and we simply draw a straight line. So for
Okay.
example, you see A bidirected to B, bidirected to C, maybe C bidirected to A. So in this particular graph, each and every edge can go both the directions. Okay. So this
So
particular graph is equivalent to draw it like this.
So in this graph, if we connect another nodes with only one direction, then also we'll call them as undirected one.
No. See, even if you have one edge which doesn't have both the directions, so let's say like this only.
Yeah.
So like this. Now this will become a directed graph.
Okay.
Okay. So even if you have one edge which has only one direction. Okay. Now BD is an edge which has only one direction. There is no other direction. So therefore, this will be a directed.
Okay, but the same thing when we just only opposite when we do in the another picture where A to F having the both direction, but A to B has only the one direction. Then we can't call it as undirected. We will call it
This is a
directed.
directed graph. See, in your graph, even if you see one particular edge which has only one direction,
yeah,
that particular graph is the directed graph.
Okay,
All
got
the
it.
edges should be bidirectional. So that we can actually remove those directions and we directly write it like this.
Okay.
Draw it like this.
Okay.
Okay. Understood. Now this is a directed graph.
Yep.
So now we are interested to find in degree.
Sorry to interrupt you, sir. So we should have n minus 1 edges, maybe bidirectional.
Why n minus 1 edges?
Hello.
You are
Sir,
talking
am I
about
audible, sir?
Yeah, you are audible. You are talking about a tree.
No, not tree, sir. I mean, you just told no, sir. That is in the second graph, A, B, C. 3 are bidirectional and only B to D is there, only one way. So by default, we can assume that in a graph, if there are n edges, then we should, if there are n minus 1 edges are bidirectional, doesn't matter. It is a directed graph.
In the other ways, like don't look at the n minus 1 bidirectional edges, look at the one directional edge.
Okay.
Even in your graph, if you have one directional edge, then that particular graph becomes a directed graph. Okay, you forget about how many bidirectional edges are there. You only concentrate on single directional edge. Even if you see one single direction edge in your graph, then that particular graph becomes a direct.
It's a directed graph.
Yeah.
Okay, sir.
Okay.
Clear. Thank you, sir.
Okay. Now let's come. So there are two interested things for every vertex in a directed graph. One is in degree and out degree. And in degree and out degree will be for every vertex in a directed graph. So this particular vertex will have one in degree and one out degree. And this
So-
particular vertex B will have, yeah.
Two
So,
out degrees, sir.
Sir, total degree, we can say total
Two out
degree
No,
A
no,
has
no,
a
no,
two.
no, no. That is a bad thing to say. So that is not a good thing. Not good thing. That is another kind of thing. There is nothing called total degree in a directed graph. Total degree of a vertex in a directed graph. There is nothing like this.
So we have in degree and out degree.
Yeah. So this is wrong. There will not be any total degree term in a directed graph. Remember this. So if it is a directed graph, we use the terms in degree and out degree separately. There is no total degree which is equal to in degree plus out degree. There is nothing like that. Okay. If it is undirected graph, you will have a degree. Understood? If it is undirected graph, there will be only one term associated to each vertex, which is degree. But if it is a directed graph, there will be two numbers we will assign to each of the following vertex. One is called in degree and other is called out degree. Understood the difference?
Okay.
Sir, for each vertex it varies, no, sir? Depends.
For each vertex, the value for in degree and out degree will vary according to
According to the graph given.
Yeah. So what is in degree means? So in degree means
Edges coming inward.
Thank you, sir.
Number
Towards that vertex.
number of edges coming towards the vertex.
Is total
Or-
number of ones according to column.
Hmm?
Addition matrix.
What?
Number of columns, total number of one in a column coming to adjacent matrix.
Correct. In an adjacency matrix, you can count the the column corresponding to that vertex. Or you can simply say number of incoming edges. So that is, if you count the number of incoming edges, so that will be the in degree of that particular vertex. And out degree is completely the opposite one. Degree will be number of edges going from the vertex, or simply number of outgoing edges. Okay. So you count the number of edges that is going outside to that particular vertex, and that number will be the out degree of that particular vertex. So understand this, and let us compute the in degree and out degree of this particular vertex. So in degree, I will write it with blue. Out degree, I will write it with green. Okay, I will compute for one vertex. You tell me for the other vertex. So let me compute for vertex B. So for the vertex B, there are three edges connected to vertex B, out of which one is coming towards B and two are going outside to B.
One is the
Yeah. So the in degree will be, if I
one is
see the correct. So the number of edges that are coming towards B is only one. So this particular edge is coming towards B. So the in degree of B is
One. Out is two.
Yeah. And similarly, the out degree, if I want to compute the out degree, I will see how many edges are going away from B. So starting from B and going to other vertex. So this is one edge and this is another edge. So there are two edges, two outward going edges from B. So therefore the out degree is 2, the in degree is 1. So tell me the in degree for vertex D.
2.
2.
2. So you can see 2 edges are coming towards D. Yeah, Kajar is.
And
No,
one
no,
is
I just want
out
to
degree.
answer, nothing else.
Okay, okay, you want to answer.
And
Okay.
one is out degree, no?
And what is the out degree of vertex?
1.
1.
So only one edge is going outside of D to E. And similarly, you can compute E. So for E,
Yes.
what is the in degree?
1.
So it is coming.
2. 1, 2. 3.
3.
Total 3.
3.
Total 3 are coming.
All of them are
Okay.
incoming.
So
And
only
one is
out
out
degree.
degree.
and what is the out degree?
Only 1. Towards F.
Yes, one out degree you can see here. It is going, one edge is going towards F. So in degree is 3 and out degree is 1. Similarly, we can see this thing also. For F, the out degree is 1.
2.
3 is 2.
Yeah. So
In
degree
is 2, out is 1.
Is
out
1.
degree,
2. Out is 2.
Out degree 2.
In 2, out 2.
yeah,
A and E.
F
from
to E,
F
F
to
to
E,
E.
Both are 2.
F to A and F to E.
Yes,
So there
sir.
are 2 out degrees. So we have computed these things. A and C are left. So what is the in degree for A?
1.
1.
1. What is the out degree of A?
2.
2.
3.
2.
3. Sorry, 3. F
So to E,
is also
to
there.
B, to F also.
3.
Yes.
3.
3.
And for C?
1, sir. In degree 1.
1 in degree, 1 out
1
degree.
in degree
One
and
out,
1 out
one in.
degree.
That's it. So each and every vertex will have an in degree and an out degree separately for a directed graph. If it is undirected graph like this, there will be only called degree. There is nothing in degree and out degree. So for an undirected graph, each and every degree of this particular graph is 2, 2 and 2. So for undirected graph, we simply define degree is the number of edges incident to that particular vertex. So there are 2 edges incident to this particular vertex A. So it is 2, 2 and 2. So this is called degree. So never confuse. For a directed graph, there will be in degree and out degree separately. And for undirected graph, there will be degree. Okay. Okay. Chalo. Now let's see what is BFS tree. So BFS means breadth first search. So what is this actually means is, in any given graph, this particular graph is explored. So we will explore the graph by levels. Okay, what we do is we start from one vertex in a given any graph. Let me take the example and that will be much more clear to you, I guess. So let us take one example, whether it is directed or undirected, it doesn't matter. So what shall we take? Directed or undirected?
Indirected.
Sir, we will take directed, sir, because in lecture we have used undirected.
Acha, we take directed graph.
Yeah.
So okay, let me draw the graph. So let's say A, B, C, D, E, and F, and G maybe. Okay. So I have taken 1, 2, 3, 4, 5, 6, 7. 7 vertices. This is a graph. Okay, I will take directions to this first. How many of you have seen directed acyclic graphs?
I have seen.
See, sir.
Yes, sir. DAG.
DAG.
sir.
Okay.
Yes.
Okay, I have taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7. So there are 7 vertices and 10 edges, 10 directed edges.
Sir, why we cannot join E and D?
No, there is nothing nothing like why we cannot. We can. That will increase one more edge. That's it. So there will be 11 directed edges. So this is my graph. I have taken this graph. Okay. So let's say I have this graph to me. What I will do is we wanted to explore this graph. Like we start from one vertex and we explore that particular vertex and we move to the next vertex via these edges.
Sir, we do explore in alphabetical order.
If nothing is mentioned, you can do in whatever way you want. Okay, whichever edge you are interested, you can take it that way. But if it is mentioned that you should follow alphabetical order or numerical order, then you should follow that method. Okay, let me impose another condition also. So we are doing this first search starting from node A. So you should start from. So if you want to explore any graph, you should start. There is a starting point, right? There should be a starting point to start.
So we can call it root node.
Yeah, that is the root node. See, there is a root is something like there is another technical term called root vertex. So root vertex is basically another term. Okay, root we cannot.
In question I see, that's why I asked.
In question you have seen. No?
Yeah, there is a question from root node.
Kaha? Where did you see question?
No, it's not
Activity questions.
rooted.
Maybe that is rooted at
Rooted
node.
at A or B.
Rooted is different from root. So root vertex is another thing. But you think it like a starting point, okay, starting node, or for every tree there is a root, right? Yeah. So that is how they might have said. So okay, there should be if you wanted to explore or if you want to do any task or anything, you will start from one thing, right? So that particular starting is even in our breadth first search, what we do is we are exploring this particular graph, and there should be a starting point. So we choose that starting point, and let's take the starting point to be the node A or the vertex A. So we should start from here and traverse. Traverse means you go along the graph, traverse the graph in alphabetical order. Okay. Now what we have to do is we are at vertex A now. So now we are standing here. So from here we are going to start and explore this particular graph completely. So what breadth first search says is, as you are starting from vertex A, what you do is you explore all its neighbor vertices first. So you explore all the level 1 vertices. So what we do is we start from vertex A here. So this is the BFS tree. So this is the graph, and we are going to compute the BFS tree, breadth first search tree. So what we are going to do is we are starting from here, and we treated this as a level 0. So that means the distance from vertex A to vertex A is 0. So no need to travel any edge in order to go to vertex A if you are at vertex A. Understood this point?
Yes, sir.
Like if you want to go to vertex A and you are at vertex A, there is no need to travel between any edge. So no need to travel, you are at that place itself. So that is why this is treated as level 0. And what this breadth first search says is you explore all the vertices which are neighbors to A. So what are all the neighbors
B,
of A?
D,
B,
B, D, E.
F, D.
B,
E, E, D.
correct. So yeah, so from A, so neighbors are nothing but the vertices which share a common edge, which shares an edge, the very next. So by traveling one edge, I can reach them. So those are the
Adjacent vertices.
adjacent vertices. Correct.
Sir, we should take a Q for this, no, for BFS.
What is Q?
Q. The first we take A, then we have to place B,
So the first
D,
in, first
E.
out Q.
Then we.
I didn't understand. What is Q?
So that Q where we place the vertices that were visited, and then we suspended vertex we can explore.
We
The
don't
method
suspend
to
in
write
BFS.
algorithm, sir. Stack, queue, B first follow.
This is we
I
need
know
Q.
suspended is not happening in BFS. It happens in DFS. I guess.
Yes, it's in DFS. Yes.
Okay. If you wanted to bring the technical terms, okay, you can bring. But I don't think there will be.
This is showing in the lecture.
Yeah, I understand. I understand. So what professor has done is like something like he has marked this as visited. Is that what he did, right? That is what.
Yes, visited. Then
Yes,
they will include the visited vertices. Then they will remove the vertices from where the visited vertices are there. Then again, explore the next one.
That is what we are going to do here also. So now we treat this as a visited vertex or the vertex which we explored already. You are starting from here and you know what all the things are here. So you know everything about A, vertex A, and you wanted to go to the neighbors of A. So as we said, you should travel along the alphabetical order. First you will go to B and you will explore, then to D, you will explore, then to E. So now what you do is you just cross out this A so that you have seen this A and take that A in the level 0. And next thing you have to do is you have explored B, D, E. So you have seen B, D, E because they are the neighbors of A, and you take those neighbors in the level 1. So this is B.
Yes. Sir, starting node is called root, sir.
I'm not sure about this root. See, root vertex is something from where I start. So if I call this particular vertex as a root vertex, then it says that I can travel every vertex in the given graph. So that particular vertex is called a root vertex. Understood?
Okay, sir.
So if I take that particular vertex, I should be able to travel every other vertex in the given graph. So if I can able to travel like that, then this particular vertex is called a root vertex. So that is the technical term we use for root. Root is used for that. And I am not that sure about this root vertex can be called as this level 0 vertex. I will just check and let you know. Okay. So whatever I know, I think the root vertex is the vertex from which I can travel every other vertex in the graph. Okay. Okay. This is B, D, and E. Okay. Now you see all these three vertices comes into the level 1. So that means whatever the vertex which are in the level 1, you can travel from vertex A by taking only one edge. You can travel to this particular vertices B, D, E. That is what this BFS says. So that is why this BFS explores level by level. So it actually explores one length far away vertices, then 2 length far away vertices, then 3 length far away vertices. That is how the searching happens in the graph. Understood? So you can actually find the minimum distance using this BFS. So you can actually find the minimum distance from A to G by using this particular BFS. And then you can identify if G comes in the third level, that means the minimum distance is 3. At least 3 edges you should travel. That should be like, I will explain it later also. So from now what we did is we explored B, D, E. Now, as I said, we have to traverse the graph in the alphabetical order. Among this B, D, E, we mark B as visited now. Now let's come back to B. And now we are here. Came here and we mark B as visited. And we explore the neighbors of B, which are unvisited. Unvisited neighbors of B. So what are all the unvisited neighbors of B?
C and F.
C and F. So this is visited. Anyway, this is not a neighbor because there is no edge going backwards. So only neighbors are C and F. So I can go to C. If I am at here, this place, I can travel to C or I can travel to F via these edges. So therefore, from here to C, from here to F. Okay. Now I explored B. Now my next target is to explore D. So one level 1 vertex is explored.
D will be G, means D will reach G.
Yes. So now let's come
Only
to
G.
and mark D as visited and check for the vertices which has unvisited neighbors. So who are all the unvisited neighbors of
Only
D?
G.
Only G.
Only G.
Only G. So we will draw an edge to G. And we are at to explore E. So now what you have to do, from D to you go to E and mark E as visited and check, are there any unvisited neighbors of E?
No. G is already visited.
There is
D.
only D, but D is
already visited.
Yeah. So no need to worry about that. Now let's come back to B and C here. Now we have 3 vertices which are in level 2. So these all 3 vertices are in level 2. Okay. Now explore C. So start with C now. So mark C as visited.
G and F.
Are there any vertices which are not?
Yes, this is G and F.
G and F, but G and F are already visited.
Yes, there's no unvisited matters.
Unexplored.
Right.
Explore, visited. Both are 2 different words.
Oh,
So F
yes.
and G are explored.
This was not explored, but visited.
Sir, we cross term when vertices when we explore or when we visit. When to cross the term? When we visited or when we explored?
Visited.
Okay, sir.
Okay. You explore the neighboring vertices, and once you explore the neighboring vertices, you visit one of the vertex. Okay. So right from the starting itself, what we are doing from A, you explored what are all the neighbors of A. Okay. Once you know there are 3 neighbors, then in alphabetical order, you went to one neighbor. So which is B. Okay. From here to here I went. But I know. So it's like, see, you are in Delhi. Maybe you are in Delhi. Okay. And you want to explore India. And you want to go in an order. And you have 3 ways to go. You can start from Delhi and you can go to Agra first. Or you can start from Delhi and you can go to directly Allahabad first. Or you can directly go to Jaipur first. And you know these are the 3 places you explored. That means you verified that these are the 3 places I can start. And among these 3 places, you will visit one place first. Okay. So that is what we do. So once you explore, you write those vertices in these levels, and you visit one vertex and you explore the edges, neighbors of that particular vertex. Yeah. So now
okay,
G
sir.
and F are explored.
And when there is no edges left, then we will just cross out that.
Right. So now, see, no need to do, I guess. From now you can see if your tree has all the vertices, then no need to do all these things. Even if you do, you don't get anything. You see C, I visited C now. I am at C. But I explored G and I also explored F. Correct?
Yes.
So I can move forward and I can go to F. I can go to F and I mark F as visited. And I explore
All are explored.
All are explored anyway. So from here I will move to G. Finally I will
G
come to G.
has no root.
Even I cross out G. So this is the BFS of this particular graph. So if this is the graph, the corresponding BFS of this particular graph starting from node A is this. If I start from somewhere else, like maybe C. So what if I start from C? What if I am at maybe Bhopal? Now I am at Bhopal and I can go. I don't have any means to go back to Delhi. So from C, if I wanted to explore, what will be the BFS graph?
C to
EGF.
C to EGF.
Yeah. See this particular graph. Let me take it down. Okay. Now let me mark with red. So I am at C here. Okay, I am starting from C and I am trying to do the searching using BFS algorithm. So how will I proceed? I will mark this C as visited
Neighbors of C.
And
and
it's level
explore the
0.
neighbors of C. So what are the C neighbors?
E,
F, G.
F, F, G, and E.
EFG.
What is the
E, F,
link in
G.
here?
Only E, F, G. So
E,
this,
F, G.
yeah, this is E, this is D, this is G, this is
So thank you, sir. Numbers, letters are not clear. That's fine.
okay. So now tell me this is C. So we mark C as visited and there are three neighbors which are E. In
E, F,
alphabetical order, it is E,
F,
G.
G.
F, G.
And C is also in level 0.
Now C is at level 0.
Yeah.
Okay, you are at
G
C.
is at level 3. EFG at level 1.
And
Now
these three are in level 1.
So these three are at level 1. And now EFG, which one is alphabetical order? E is the next vertex.
Yes.
I have to go. So now from here I will come to here. And I mark this E as visited. And I explore the unvisited neighbors of E.
That is
What
D
are the
only.
D.
D.
Sir,
D?
I have one question. Every time we start with the smallest first, like E, F, G. If we start from G, what will happen? Like
If you start from
G, no, suppose starting node is a C. After that, the neighbor of C is E, F, and G. We start after from G. We explore the G.
You can visit G, but my condition is you have to go in the alphabetical order.
Okay.
So
this condition is given that will
is why I'm
happen.
going. If not given, you can explore E or F or G, whichever you are interested. Okay. As it is given, I have taken E. That's it.
So, sir, if we run this algorithm in random, so it can give any random number first, like.
No, if we have given an ascending, saying ascending order, then we have to consider that ascending order, like 0, 1, 2, 3, like that.
No, when
it's not defined. Not defined.
If it is not defined, there will be different BFS trees.
Yeah.
Different.
Okay.
Like that, the same condition as C.
I guess you have one of the graded assignment or practice assignment.
Yes.
So we haven't mentioned the order. We just asked the possible order of the vertices you visit. Something like that, right?
Yes, sir.
So
Yes,
it's
sir.
an MSQ. That means you can either visit some vertex or you can visit the other vertex at the same time also. One may come front or one may go backward, like that. So if the order is not mentioned, you can. So now
in that sense, yes, sir. First you complete that.
Yeah. See, this is what. See, from E, the unvisited, the unexplored vertex is D. So I will take D in the level 2. Now after E, there is F. So I go to F. Okay. So from F, I mark this as visited. And what is the unexplored vertex of unexplored neighbor of F?
G. Nothing.
G is
No,
already
G is already there. Nothing.
Already
Nothing.
already explored.
So now I come to G. I mark G as visited. Are there any unexplored neighbors of G? No.
No.
No, sir.
Now I go back to D. Now I come back to the level 2 vertex, which is D, and I mark this as visited and look for any unvisited or unexplored neighbors of.
Excuse me, sir.
Hmm.
I'm unable to see your cursor where it is exactly. Can you please like highlight or something?
Here is my cursor.
Okay.
Okay. So D we have visited. We are done. If I start from C, I cannot go to B. You have to observe this. I cannot go to E.
Yes.
Okay.
That's why we are using this alphabetical order.
So you see this comes in the level 2. So now you
Sir,
see
here,
if this is a
if
BFS.
sir, if direction is not given, in that scenario we can able to explore A and C.
And it means it is undirected graph.
This is a
Sir,
directed graph.
is it not a condition that we have to visit all, sir?
It is not a condition. See, it's like
sometimes it's possible that here A and B are not visited.
Yeah, here A and B are not visited. So if I start from C, I can only have these many vertices.
That's it. Okay. Thank you, sir. That is my doubt, sir. Actually.
Yeah. See, that
by any means we can't visit all the vertices. Yeah.
So what will be the
Thank you,
forward edge in this?
What will be the
Forward edge?
Forward edge यहाँ क्यों आएगा?
So tree में ही होता है.
इसमें नहीं आएगा. BFS there is no forward backward cross. There will be forward backward for DFS.
DFS.
Okay.
So
there are few conclusions we can draw, and these are the main important things for this algorithm. So first conclusion, basic conclusion is this BFS tree explores
every vertices
level by level. Okay. So wherever you see, in which level you see D is shown in the level 2. So that means the minimum distance from vertex C to vertex D is 2. Okay, at least you have to travel 2 edges in order to reach from C to D. So what actually it gives is, if you draw the BFS tree, it actually gives you the shortest path from the starting vertex to every other vertex which are reachable. Okay, understood this?
Yes, sir.
If from the starting vertex, which all are vertex which are reachable, so it gives for all the vertices, it gives the shortest paths.
So how it gives the shortest path?
See, this
We
is
have
how.
to traverse to the
This is how. If you see the levels, it will give you the shortest. So in order to reach E, F, G, the shortest path is of length 1 from C. And in order to reach D, the shortest path is of length 2. So whichever level it comes, the vertex comes, that many edges.
But it is dependent on how we start our BFS. If we have started it from A, then we can directly reach the D point, and then it will be the shortest way. In that
you
sense.
Start from
the point of exploration is A, then we can directly reach D. Is what you say.
See, that is different, right?
So
that
how
is why
can
I
it
said
be
it gives the shortest path from the starting vertex to every other vertex which are reachable. Okay.
Sir, I have one more question. If we have undirected graph instead of the directed one in the same scenario, then we will also include B in the exploration.
That we will do, but follow these conclusions first.
Okay.
So second conclusion is, so you see here, if A is the starting, my D comes in the level 1. Okay. Observe this. Depending upon the starting vertex, your BFS tree varies. And whatever this conclusion I made is on the starting vertex. So this particular BFS tree provides us the shortest path from the starting vertex to every other vertex which are reachable. And the second one is this BFS tree. If you compute the BFS tree, it gives me, so it tells what all the vertices are reachable from the starting one.
It tells about reachability.
It tells about the reachability. Correct. So if you are starting
These
from vertex
conclusions-
C, so in this graph, C can, if you are at C, you can only reach E, F, G, D, but not A and B.
Yes, sir.
So that this particular BFS tree, there is no A and B. So by looking at the BFS tree itself, you can guarantee that you cannot travel to A or B if you start from vertex C. So this actually gives you the reachability also. Okay, but if you start from vertex A,
these conclusions that you're drawing are these are the applications that Professor
these are the applications you can use. Correct. Okay.
Sir, how we can find cycles in BFS tree, in graph from BFS tree?
From the directed one, we can find.
I don't think. See, from BFS you cannot. From DFS you can.
Sir, in lecture, sir told if this branch is not BFS tree, that means it's in a cycle, something like that. I don't understand it properly. What this means?
Not DFS is that.
That is DFS, I guess. So if you have a
BFS,
backward
not
edge,
BFS.
if you have a backward edge in DFS, then that gives you, that tells you that your graph has a cycle.
So please,
For
please how to
directed one, for directed.
Tell for.
So yes, please
For
tell how to
One
find
example.
the forward and backward edges in DFS tree.
Directed.
We will go. One example for undirected. Let's do for undirected.
Undirected.
I will just make this particular graph as an undirected so that you can correlate what happens when it is directed or undirected. Okay. So
Okay,
these are the two conclusions, and one more is an application. So basically, you can actually predict the original graph using BFS. How?
We have question on this.
Yeah, we have question on this. This is one more application. It actually says only prediction, not the exact graph. You cannot get the exact graph, but you can predict, yeah, this may be the graph or this may not be the graph, and particular vertices cannot have an edge between them for sure.
Yeah, please give some example for that. Like, how can we predict that there can be an edge and there cannot be an edge for it?
Okay, I will come to this after dealing this undirected also. We will come to this. We will come back to this. Okay.
Sir, in assignment, there is one question like in BFS tree or also in DFS tree, that which one is cannot be the edge. So
Yes.
how to find that one?
For that thing only, I will come back. Just we will take some 5 more minutes. Let's discuss the undirected BFS, undirected graph ka BFS tree, and we will go there.
Sir, one thing here. In a lecture, sir uses the Q for BFS.
Uses?
Uses the Q.
Q.
So the question is it necessary to we use the Q, or we can, why we use the Q?
No, it's not necessary, but it's like if you are using computers or anything, for there it will be helpful. But the basic idea is how this BFS is performed, you should understand.
Okay. Another one thing, question. In BFS, we sir uses the queue, and in DFS uses the list. Stack. So we can interchange it. we can use the stack in a BFS and queue in a DFS.
No, that won't work.
So why, sir? Can you
So that
explain
is
it
how
after?
this searches happens. Okay. So
see, EFS and BFS are concepts. Stack and queue are actually concepts. You know, there is suspended and visited. These two are separate things. These are the main concept that is running this queue and stack. So basically, stack and queue are nothing but concepts. It is not that data structure that you are talking about, that vertical bar of box. It's basically the concept. So
Everything is a concept here. Just I'm asking why.
Because in DFS we suspend the queue we visit, and in BFS we don't suspend that. We continue with that. So that is the difference between stack and in the queue.
See the way which the algorithm performs.
The question about this was that whether we can interchange queue and stack. Yeah, my point is that if you interchange the queue and stack between BFS and BFS, the order which you get the output will be different. So we cannot interchange stack and queue between BFS and BFS. Yeah, it is just a concept which has been used in the lecture to explain you. But yeah, here he's just explaining us easily how we can convert this graph into a tree. So this is more helpful.
Okay.
that thing is useful in computation. If you do it by computer, then it will be helpful in that order. But here means there are two types of graph theory. It is one for computation and one is for mathematics. We are here learning for mathematics, but sir is also teaching us for the programming perspective. That is the main thing. That's why he is using stack and
queue.
You will see more data structures like those later.
Okay. Shall we?
Yes, sir.
Okay, now this is an undirected graph. Okay, the same graph, I just remove the directions to every edge. And I am starting from node A, and the order also follows the same thing. So let's say alphabetical order. Okay, how will be the graph? BFS tree. So A,
B.
Now I explore the neighbors of A, which are
B, E, D. B, D, E.
As I said, alphabetical order.
Yes.
As I said, alphabetical order, it is like B,
B, D, E.
B, D, E.
Correct. So this is, we mark it at level 0. And this is level 1. And now I visit B. And I mark B as visited. And I explore the unexplored neighbors of
C and G.
C and G.
C and G. So C and G. So I will write it in the alphabetical order. C and G. Now I have D. So yeah, the same thing we have. You see, if you wanted to talk about the queue and stack, what is queue basically? So 1 comes in, 2 comes in, 3 comes in, first out. So do you understand this concept? First in, first out.
Yes, FIFO and LIFO.
So this process is actually used in queues. Correct. So if you are in movie theater or maybe in the bank, so whoever is in the first position, his query will be get satisfied first, and next one he will go out. The second one will go into the first place. So first in, first out. Yeah. So first in, first out is what called queue. So here also BFS does the same thing. So we started from A. We kept A at the first position. And next we explore the neighbors of A, which are B, D, E. So alphabetical order, it comes like B, D, E. So now you see So A is in the first place, B is in the second place, D is in the third place, and E is in the fourth place. Now this is the order in which we visit the neighbors, visit the vertices. So you see, we visited A first and we marked it with blue cross and we kept A at level 0. Similarly, we explored BDE and we added that BDE to our queue, and this BDE to the level 1 of our BFS tree. So this is the BFS tree. Okay. Now A is visited, A is satisfied, and A left out. So A went. Now B comes to the first position. So what happens is A left. Now B comes to the first position. So now B should be visited. So this is what BFS algorithm works, as well as the queue also, that this particular data structure of queue works like that, first in first out kind of thing. So the same thing is being worked here also. So that is why we relate queue with BFS. Okay. If you take it like stack, what is stack? First in last out. Correct? What is stack?
Sir, if
Yes,
we
sir.
take
LIFO,
BD,
last in first out.
Last in first out.
Last in first out.
Last in first out.
With the same example, we can take like evil, equals.
So the last in first out, if you are stacking a books continuously, so the first book you stack is at the bottom, the second one will come above that, and third one will come above the second one. So if you wanted to remove, you start removing from third, second, and finally first. So which one comes at the last? So the third book. So let's say this is book 1, on top of it book 2, book 3. So book 3 came at the last, but if you wanted to remove, you should remove book 3 first, then book 2, then the bottom one book, first book. So which came first will go out last, which is not the correct way. The correct way is last in first out. Huh?
We are backtracking the thing.
Yeah,
First, we are taking out the last one, and then we are taking.
Yeah, correct. So this particular thing will be followed by DFS. So we will deal with DFS also. Let us compute this thing. So CG, and we have to B is visited now. Now B will go out. So in the queue we have D next. So we have to explore D. Or we have to visit D. So D is visited. Now we are at D. Now we will explore the unexplored neighbors of D. So what are the unexplored neighbors of D?
C and E.
No, everyone is explored already.
Already explored, right? C and E.
Yes.
Okay. So there are no unexplored vertices. So D calm ho gaya. So even he will go out. And E, already CG came, right? Now CG will come into the queue. Now E is there. We will go to E and we will explore E. So when I see E, so when I visit E,
F only is there.
what is unexplored vertex?
Only
F.
F.
Only F.
So F comes into our BFS tree now. Okay. Now E is visited. E will also go out. So these all will be removed. And C comes to the first place. So this is how it will be. Now C, G, and F comes to the queue. Now C should be visited. So if I visit C, what are the unexplored neighbors of C?
Nothing left.
Nothing left, sir.
Nothing left, right? So C will go out. Now G comes in. So G should be visited. After visiting G, so what are the unexplored neighbors of G? Nothing. So G goes out. Finally, there is only one vertex left in the queue, which is F. Once I visit F, the last vertex is visited now.
So all are visited.
So all are visited and our BFS tree is complete. So this is level. So now you see this is how the BFS tree, if I start from vertex A. What if I start from vertex C? starting from node C. So this is C, B, G, F, E, D. So what are the who are all the neighbors of C?
B,
D, F, V, G.
D, F, G.
B.
D is also.
D,
There is B also.
yes, D,
B,
D,
D,
F,
F,
G.
G. Correct. So now, okay, here I will write the Q also. So now you see the Q. So C, B, D, F, G. So this is how the Q is. Now C is visited. I will mark C as visited. And I will visit the next neighbor vertex of C in alphabetical order. So I
B.
should go to B. So C
B.
goes out. Now B
B,
comes.
there is only A because C and G already visited.
So B,
Explored.
I will mark B as visited. And what is the unexplored vertex
A.
of B?
A only.
A only. So that A
Because
comes
C
in.
and G already visited.
Yeah. So this is A.
Explored, sorry, not visited, explored.
So yeah, this is A. So here A comes in the level 2. And I mark B as visited, and B goes out of the queue and A adds into the queue. So after G, A comes. Now I have to visit D. So once I
Then
visit
E.
D, so what are all the unexplored neighbors of D?
E.
E.
E. So E comes to the queue. D is marked visited.
So D will go.
D will go. So E will come here. Okay. Now you see this is the BFS tree. So because all the vertices are already present, there will not be anything more.
Yes, sir.
So
Yes,
nothing to do.
all
So you
particles
can
are
stop.
visible.
Once you have
Explored.
all the vertices, you can stop there itself. There will not be any new. Okay. So everything will be visited and nothing, you won't get anything from all the visiting things. So this is what the BFS tree will be. Now you see this is different from what we got earlier. So this is different and this is different. Now we have 4 vertices in level 1. So this is level 0. This is level 1 and this is level 2. So you see this BFS tree is different from this BFS tree. So depending upon the starting point, our BFS tree changes, and what it gives is common. So you see if you are at A, you see if I wanted to reach G from A, the shortest path is A to B, B to G. You can check A to B, B to G. So this is the shortest path. And there are other paths also, A, D, C, G, A, B, C, G, like this, A, B, A, D, E, F, G. These are all paths to G, but the shortest path is A to B, B to G. And it's of length 2. So your G vertex came in the level 2 of your BFS tree. Like this, from this particular vertex A, which is the starting vertex. Any doubt? Okay. So from the starting vertex A, you can actually find the shortest path to every other reachable vertex in the graph by looking at the BFS tree. So in order to reach B, D, E, you can take only one vertex. So you see they are all the neighbors. So you need only one edge to travel to the neighbors. And in the level 2, you see there are C, G, F. So if you want to reach G from A to B, B to G. If you want to reach C from A to B, B to C. So this is the shortest path. And also there is a shortest path A to D, D to C. It won't give you how many shortest paths are there, but it gives you the shortest path length. So 2 is the minimum length required in order to reach to C from A. Understood? So this BFS tree has these many applications. So you can infer from this BFS tree. Am I audible?
Yes, sir.
Yes, sir.
Yes, sir. Very much.
Okay. Understood about this part?
Yes,
So
sir.
how you can actually get the shortest path from the BFS tree?
Yes, sir. Yes, sir.
Yes, sir.
So this
Very
gives
clear,
the
sir.
shortest path. And also one more thing is reachability. It tells you the reachability. So if this is an undirected and connected graph. So from any vertex you can reach any vertex. So in your BFS tree, it actually will have every vertex if it is undirected. If it is directed, sometimes you may not have all the vertices. So whatever the vertices are there, those are all the vertices which are reachable from the starting point.
Got it, sir.
Sir?
Let's see this thing. Huh?
Sir, by seeing BFS tree, which cannot might be the edge in the actual graph.
That we will look at now. That we will see now. Okay.
Okay.
So we will see now. So let me take BFS tree directly. So let me draw a BFS tree. Something like this. B, C, D, E, F, G, H, I, and maybe J. Okay. My BFS tree. So how many levels are there in this BFS tree?
4.
5 levels.
5 levels.
5 levels, sir.
0, 1, 2, 3, 5.
Okay. 4, sir.
This is level 1.
4.
And
4.
4.
2. Level 3.
5 levels.
Level 4. So if you include 0 as one level also, it will be like 5 levels. Okay. So now this is the BFS tree of some graph, let's say. This is actually like this is true. What we know is this is BFS tree. So if this is BFS tree, so whatever the conclusions I said, so let's recall those conclusions. The shortest path can be found by looking at the BFS tree. So what is the shortest path from A to I?
A to I.
I.
Okay.
A to B, B to F, F.
BFI.
ABFI.
Yeah.
First level number, right, sir?
Let's level number. Yeah. So can
So level.
okay. Now my question is, can A have an edge with I?
Sorry, sir.
No, sir. No.
No.
Can A?
Sir, didn't get your question. Can you please repeat what?
Can vertex A have a direct edge with
No.
I?
No, sir.
No.
Oh, okay.
If it has a direct edge, where should this I come?
Level 1.
Level 2
Level
or level
1.
1, sir.
Level 2 or level 1?
Level 2. Level 2 or level 1?
2.
Level 2. How can that be level 2?
Level 3,
It
sir.
can be level 1, sir.
Only for level 1, sir.
Only level 1. Then
Only
it will
level
be
1.
direct.
In an original graph, if there is a direct edge from A to I, so
It will be in level 1.
It will be
we
level
visit
1.
A,
Level
we will
1.
explore all the neighbors, right? All the neighbors.
Yes.
When it comes to all the neighbors, this particular I should be in the level 1. But we know that in this particular BFS tree, I is at level 3.
If there is a level mismatch, then it will not be.
Can I say that?
So can you please explain it again?
This is not
Sir,
possible.
I'm not
Yes.
also able to get it for the
So what am I saying is,
concept topic.
if there is a direct edge from A to I, when I visit vertex A, as I am starting from vertex A, I will explore all the neighbors of A. If there is a direct
Yes.
edge from A to I, then I will also be a neighbor of A.
Yeah.
Yes.
Correct. So
Yes.
therefore, I should be in the level
Level 1.
not
Level 1.
Yes.
3. Then if I is at level 3, then I am pretty much sure that there will not be a direct edge from A to I.
Yeah.
Yes.
Correct. So I can
Yes.
say that AI edge is not possible.
Yes.
Yes. Got it, sir.
Correct. Similarly, not only I, which are at more than one level above, they cannot have a direct edge with A.
Yes.
Right,
Yes.
right.
Yes.
A to E, A to F,
A to G.
like this. So these all are not possible edges in my original graph.
Yes,
Yes.
sir.
There.
A to H or A to J. There are many edges like this. So the red colored edges are not possible edges.
Yes.
Yes,
Okay.
sir. Just like
Okay.
B to J, and there are lots of possibilities.
Right. So now from A, these are all. So there are more actually. A to, what is this? L. So this is L.
I, L. Yeah.
That is L. That is L. So this is also not possible, and also there is one more.
A to M.
This is also not possible. This is also not possible.
So it is
Right.
Okay.
Yeah.
Yep.
So these are no edge is possible in my original graph. I am sure about that.
Right.
Okay, let's move to the next level. So let's come to level 1. So once I visit vertex B, what I am doing, I will explore all the
Neighbors of B.
unexplored
Unvisited
neighbors of
yeah.
unexplored neighbors of B.
Yes, sir.
Okay. If suppose there is an edge between B and I in my original graph, let's
Then
suppose say if there is an edge between B and I, then the shortest path from A to I will be like A to B and B to I.
Right.
Yes.
Yes.
So that means the shortest path from A to I will be 2. That means
Yes,
I
sir.
should come in the level 2.
Level 2. Yes, sir.
But it is in level 3.
3.
So what it tells me?
Not possible.
There is no direct edge.
Edge between B and I is not possible.
A to I, the shortest path is 3.
Yes.
Correct?
Got it.
Below 3 I cannot have. That means there should not be any path which has only length 2 from A to I. Those all are not possible cases. Okay.
Yes.
So B to I is not possible.
We are actually counting the levels. How it is 3. From B to I, are we only counting the level 1, level 2, level 3 like that, or we are calculating the number?
See, these are the levels of initially we just drew the BFS graph and we explained what are the levels, which level it comes, right? So is it not clear? The level part is not clear to you?
I am
This is
saying
how the
that,
levels comes.
no, sir, I understand that level, but I am saying that from B to that value, what I think B to E you were calculating, right? From B to A, are we calculating number of edges or just the level number at which the I is and B is?
I didn't understand what. Can anyone?
No, sir. Can't
Sir,
understand.
Can you please repeat it?
Sir, what he is asking is, are we counting the number of edges between that B to I, or
The
simply we are
level 1.
calculating the levels? That's what I understand.
We are checking for the levels only.
Yeah.
We are checking the
That's what
levels.
he's asking.
Yeah,
Yeah.
we are checking the levels. So we are trying to guess whether there can be edge between two vertices or not. So if there is an edge, what happens? If there is no edge, what happens? That is what we are trying to see. So if there is an edge between B and I, what happens is this particular I will not come at level 3.
Yes.
So I should be in the level 2.
Level 2.
Yeah.
Because there will be a shortest path from A to I, which has only length 2. Okay. So that means what it says me is there will not be any edge between B and I. Similarly, C and I. If there is an edge between C and I, then there is a shortest path of length 2.
Yes,
So
sir.
what you can actually see is, you just zoom out a little bit. If I am looking at two vertices which are more than one level difference,
There is no direct edge.
there will
Exactly.
not be a direct edge. Yeah. So if one vertex is at level I and another is at level I plus 2 or greater. Okay. So one is at some level I can be something like 0, 1, 2, 3. Okay. So if one vertex is at some level, and if there is a difference of 2 and more in the levels of two vertices, like let's say A and M, so there is a level difference of 4 levels difference. So there cannot be a direct edge. Similarly, D and K. So you observe D and K. Even D and K cannot have an edge between them. Why?
They are two units.
Because there is two
Level
edges
difference
in
is 2.
between. Yeah, there are two edges in between, and if it is having only one edge, then we can say that it has directed.
Sir, can we say
directly, and
if
we
they
can
are at
say by
consecutive
the
levels?
level difference also.
We can
Like-
conclude that. I will conclude that. Let's say. Someone is saying, Purendru, you are saying
Level difference.
More than one level. So you can use the same thing. So K is coming at level 3. So that means the shortest path from A to K is 3 in my original graph. If I had an edge between D and K, then I found the new shortest path from A to D and D to K, which is of length 2. So K should come in the level 2, which is not possible. So we already gave you the BFS tree and K is in the level 3. So if there is a level difference of more than 1, let's say 2 or more, then between those vertices, we cannot have an edge. So we cannot have an edge if the difference between the two is the difference in levels. If the difference in levels of the vertices is more than 1. Okay, understood this statement?
Yes,
you
sir.
cannot have an edge if the difference in the levels of the two vertices then we cannot have an edge. When can we have an edge then? So if this is the condition, we cannot have an edge. What are all the possible?
If there is a level difference of 1.
1 or no difference.
No
If it is in the same level, you can
Yes,
have
sir.
an edge. Okay. So what I can conclude is,
we can have,
if the level difference is less than or equal to 1, then we can have an edge.
Sir, we are just predicting. Okay.
Yeah, this is just the prediction. We can have. It's not that it will have.
Sir, how less than 1 we can have a edge less than 1?
If the level is the same level, so E and F can have an edge.
Okay, okay.
Okay.
Okay,
You can
sir.
take small graph. Okay. Let me
Can
take
have.
yeah, A, B, C. This is a triangle. Okay. This is the graph. And if I wanted to draw the BFS tree, so the BFS will be like this, B and C. So B and C are in the level 1. And also B and C can have an edge between them. So if this is a BFS tree, this can have an edge. So the same vertices can have an edge, and also one level above or one level below. Maybe C and F can have an edge. Maybe, this is maybe. It's not like it will have. Maybe these two can have, or maybe these two can have, or
Yes,
maybe G, I can have, H and G can have, like this. One level above or one level below. EI can have, or IK can have, KL can have.
Sir, one doubt there.
Uh,
Say for example, if the original graph given, there is no edge like the way you are showing. So are we saying if it is in the same level or one level plus minus, then we can have the edge? Even though
we
if it
can
is,
have.
yeah, we can have. Okay, okay.
It's not. It is. That is what I am saying. This is just the prediction we do. It's not the you are actually giving the original graph. We cannot get the original graph, but you can actually predict. Predict by cannot having edges and can have edges. This is definitely cannot have. Okay, this is for sure, but it can have or may not have. We don't know, but it can also have that particular edge, and this can be the original graph. Okay, whatever I drew now, by if you take these edges also, and this maybe this is an original graph or may not be. But this is, if this is the original graph, then the BFS is this. I can guarantee that.
So, this prediction is applicable both directed and undirected for BFS, right? Okay.
Okay. So usually we deal with undirected graphs. Okay.
Okay.
So these applications more of we deal with undirected graphs in this particular course. More of 99% cases, our more focus is on the undirected graphs. So this is about BFS.
Excuse me, sir. What is maximum vertex cover?
Maximum vertex cover.
Yeah.
There is no maximum vertex cover. It's
There
minimum
is
vertex.
Minimum vertex cover is there, Nasha.
Minimum vertex cover is there, but I don't think maximum vertex cover is what? Take all the vertices in your vertex cover.
Yeah, exactly.
Okay.
Number of vertices, we can say that it is a maximum. Yeah.
But that is not an optimal. See, that is not a optimal. It won't deal with optimal cases. Nothing like that. Okay, you take all the whatever the graph is there. You take all the vertices. That will be the maximum. But don't. Maximum is not the optimization. Minimum is the optimization.
Okay, sir. Thank you.
Okay, that is about BFS. And let's come to DFS.
Sir, I have a doubt in BFS, sir. I noted in lecture, given a graph is undirected and make it BFS tree, non-BFS tree will non-edge in a BFS tree. Sorry, sir. Non-edge in a BFS tree is a cycle in the original graph, like that.
Can you repeat, please?
Non-tree edge.
Okay, non-tree edges.
Yes, sir.
Okay.
Maybe the cycle in the graph.
Maybe the cycle in the graph, is it?
Yes.
Which
that are not required.
Which question is this? Can you be more specific about?
Yes, sir. It is told in one of the lecture video also, 10.6.
Regarding BFS, is it?
Yes, sir. BFS.
In BFS, sir.
BFS or DFS?
BFS.
Okay, whatever we discussed, breadth.
As a breadth for such tree, given original graph is undirected graph, sir.
Okay.
We make it to BFS tree.
Okay, we make it to BFS tree.
And non-edge in the BFS tree.
Okay, non-edges matlab whatever the edges we didn't take into the BFS tree. Okay.
If that edge belongs to the if that edge exists in the graph, then that makes the cycle.
Let me just understand this, the last statement. So here we see, so these are the edges in the BFS tree, and the non-edges are these. What are all the non-edges? A to E.
Yes, here
This is the non-edge.
CGF is the cycle, right, sir?
Yeah, CGF is a cycle, correct.
Yes, C and G.
Okay,
Sir, I'm
CG
confused. I will watch the lecture again, sir.
Sir, it says like any non-tree edge creates a cycle in BFS.
Yes, sir.
Non-tree edge.
Yes,
correct.
There is one.
See,
He was explaining something.
Okay, I got it. Let me tell you. See, a tree, a connected tree has n-1 edges. So if you understand the basic properties of tree, you can easily verify that. So what are the properties of a tree?
Minimal connected acyclic graph.
Yeah, minimal
connected
acyclic
graph.
Yes.
So this is connected and acyclic, and this is the minimum. So if I add one more edge to this particular graph, what happens? It will form a cycle. So you can so you have some BFS tree, you have some tree. Let's take tree. Okay, this is a tree with some 6 edges, sorry, six vertices and 5 edges. And tree has one more property is, if there are n vertices, then there will be n-1 edges. Correct?
But is this for directed or undirected?
This is undirected. We are talking about undirected. Okay. So even the lecture also the same thing what you are saying, right? If there is an undirected graph, and if I perform BFS tree, if I draw the BFS tree of that undirected graph, if there is a non-tree edge, that non-tree edge will form a cycle. So here itself you see, if I have any other edge between among these 6 vertices, give me any edge. You give me any edge.
B and D.
B and D.
BD.
Okay, BD.
B to it's okay. B to
So
D.
if there is an edge BD, then you see A, B, D, C forms a cycle. Okay. Tree is actually the minimal connected acyclic. What this tells you is, if you add one more edge to the tree, that will become a cyclic graph. So that means that will have a cycle inside that particular graph.
Sir, it means a unique path between a pair of vertices.
That means?
A unique path between every pair of vertices.
That is acyclic. Okay.
So we are talking about acyclic right now.
We are talking about acyclic. So for acyclic, whatever you said is correct. There will be only one path from any 2 vertices, and also this is connected. But you see, this is one property of tree. If you add one more edge to the tree, that particular graph will convert into a cyclic graph. And this cyclic is the graph. Tree is actually the minimal connected acyclic graph. So if you're in your original graph, if you have any edge which is not in this tree, and that particular edge will make a cycle. Okay, it can be BC or BD or FC, whatever you can check. BE, okay, even BE creates a cycle. A, B, E, C, A will be a cycle like this. Even if DE, C, D creates a cycle. So tree is actually the minimal connected acyclic graph. Okay.
Yes, sir.
So if you add one more edge to your tree, it will become a cyclic graph.
So that means we can detect a cycle in tree using BFS2.
Like, yeah, if it is undirected, yes.
Okay.
Sir, one question, sir. So cyclic graph, it is a cyclic graph in two level, right? Level is possible.
Cyclic graph is?
The cyclic graph is possible only in two level, right? For level 2 or level 0 to level 1, like A, B, C, right? We can't form a graph between F, D, E.
F, D, E. There can be a cycle, right? Here also there can be a cycle.
Can be a cycle, but it is not like given any edge between them, but it can be possible.
Yeah, it can be possible. So see, this is, take this as the graph. So if you wanted to come up with the original graph, you just draw the edges between the BFS tree only. So this is a BFS. This is the original graph. This can be the original graph. If I draw the BFS tree of this graph, what will it be? Starting from A, the neighbors are B and C,
B, C.
and X
Right.
or B. B will be F, and from F and C, if I come to C, there will be D,
E,
and E. So this is the BFS tree.
Yeah.
This is the BFS tree, and this can be the original graph.
And in trees, we can't form a cycle.
Tree doesn't have a cycle. Tree is basically, understand these three terms: minimal connected acyclic graph. Okay, it is a connected graph. So that means from any vertex to any other vertex, there is a unique.
Sir, graph or undirected graph? Sir, graph or undirected graph?
It can be anything.
Graph.
Yeah. So connected acyclic, undirected graph.
Connected acyclic. So tree. Okay, here it is undirected graph. Okay.
So what that
So
minimal means here?
For
that means zero. That means 0 degree.
No, is that means it has very like
vertices, which is vertices which is of a 0 degree, which is also called the root.
To have the least amount of edges connected there. That means
yes.
Okay, shall we move forward then? So that is what that statement is. If you have any non-tree edges in your BFS, in your original graph, so that edge will create a cycle, because if you add one more edge to our any tree, that will make a cycle. That will create a cycle.
Got it.
So this is an undirected. This is for undirected case. Okay, let us see quickly DFS also. So DFS tree. So DFS is depth. Okay, this is one more kind of another different algorithm where here also we explore the graph, but in a different way, not like BFS. So let me take the same graph then, and we will do DFS. So what else? Have you guys started week 11?
Not yet, sir.
Not
Yes,
yet,
sir.
sir.
Yes,
Not
sir.
Yes,
yet.
I
sir.
started.
Yes, sir. Started.
Uh,
You feel somewhat difficult, maybe. Like
no, sir.
no.
It is not because I completed this in CET and I completed CT, so
Oh,
that's why it is quite
okay,
easy.
okay. Then
And
you
the thing,
won't
main
feel
thing is the
difficult at all.
negative wages things is confusing. Not able to get it, the negative wages.
Mm-hmm. We will discuss. We will discuss those in week 11.
I completed all the while learning program.
Completed all,
But
everything.
yes, not everything. Means there are something that I haven't completed. In week 11, I have to see. And in week 10 also, I am seeing 2 to 3 new things like forward and backward.
Mm-hmm. So now we will see what are the forward, backward, and everything in this DFS quickly. Okay, this is the graph. And what is this ABC? Okay, unlike in BFS, we won't explore this in the level by level. But instead, what we do is we actually, it's like a greedy thing. You actually start from one vertex and you don't explore all the neighbors. You explore one of the neighbor and you will go visit that neighbor. And from that neighbor, as you are at B now, from that neighbor, you will go search for another neighbor of B. Like that, you will be like a greedy, like you just wanted to go deep into your graph. You don't want to explore level by level, but we go in depth. And once you reach a dead end, you will just come back, and you will take the other path. Like that, this will happen. So that is why this is depth first search. So it will go in deep from starting from one vertex to dead end vertex, where I cannot travel to any other neighbors. If there are no neighbors, I will stop and traverse back to the nearest junction and I will go. So what we do is, okay. So let's start. Can I? Okay. So what I wanted to do is I will start from node A. And similarly, as we will take alphabetical order. Okay. So I will start from A. What I do is the neighbors are B, E, D. So I won't explore everyone.
B.
I will take alphabetical order B, and from here to here, I will travel along this edge, and I will go here, and I will visit this. Okay. If I bring up stacks here also, it's like, so I am starting at A. So stacking, right? It's not Q. So it will be like this. So I started at A. So from A, I went to B. I directly went to B.
Yes.
So that means there will be an edge from A to B. And from B, I will add that B. I will stack that B here.
C.
And from B, I see the neighbor. C and F are the neighbor. And I choose the alphabetical order and I move to C. So from
Yes.
B, I move to C. And I will stack C.
First in, last out, right, sir?
Seat, yes.
Last in, first out.
Last in, first out.
Okay,
Last in, first.
Last in, first out.
Yeah. So A, B, C. Now I came here from B to C. So I have visited A, from A to B, B to C. From C, I see the neighbor.
So C to D is not possible. The C to E.
There is no C to D. So I see the neighbor.
C to E.
Then
Then
so
alphabetical.
I will move to E, alphabetical order. So I will move to E, and I will add E to my stack, and I will add E here. And from E,
it will.
I can only go to
D.
Only go D.
Yeah, only to D. So what I do, I will stack D and D. And you see, from D, I can go only to G.
Yes, only to G.
I have to make it what is that? Okay, so A to B, B to C. So it's like a greedy. So you won't even explore. Sahi say we don't even explore the neighbors. We just pick one neighbor, alphabetical orderly. We will go there, and we will pick another neighbor of that, and we will go there, like that from E to D and D to G. So G will be stacked here. Now what we do is, as G came in the last, we will explore G first. So now we explore G. Nothing is there. I cannot go. I cannot go anywhere. So I will remove G. I will remove G and I will come back to D. So from G, I will come back to D. And at D, I will see if there are any unexplored vertices, unexplored neighbors. Are there any unexplored neighbors of D?
No, there's no unexplored neighbor.
No, sir.
We then have to go back to E again.
Actually, sir, we have F, but there is no between edge between F and G.
Hello? Am I audible?
Sir. Yes, sir.
Yes, sir.
Yes, sir,
Okay.
audible.
Did I lose connection in between? Or?
Yeah, sir.
Okay.
I thought I lose the connection.
Okay, okay. So there is nothing with G, and we will come back to D. So G we will remove from the stack, and we will come back to D, and we will see are there any unexplored neighbors of D?
No.
Unexplored neighbors of D?
No, sir. Then
Back
we will
to
go
E.
back to E.
So we will remove D and we will go back to E. Are there any unexplored neighbors of E?
No.
And we
Well,
will go
back
back
to
to
C.
C. And once you reach C, you see are there
Yes,
any
now we
unexplored
have unexplored neighbor.
F.
F.
There is a vertex which is unexplored, and we will go there.
And this one is the last.
Yeah, from C to F.
Right.
And after there are, and once I reach F, I will see are there any unexplored vertices, neighbors of F. So there is G. G is a neighbor, but G is already explored. Already came and visited. It came into the DFS tree. So there are no unexplored vertices. So we will go back to C. So F comes here.
Sir, DFS tree will means executed only for directed graph, no?
DFS is only for directed.
Okay.
So F comes in and F goes out directly. It comes in, there is nothing, so nothing need to be visited or explored neighbors of F. So it goes out and it comes back to C. And now there are no vertices which are unexplored of which are neighbors of C. So C will also be removed from the stack and we will go back to B. Doesn't have any unexplored vertices. So B is also removed from the stack. And finally we have A, and A also we don't have any unexplored neighbors of A. So A will also be removed from the stack. So this is how it will. So this will be the DFS tree.
Sir, why can't we have DFS tree for undirected graph, sir?
Yeah.
In the lecture, it was undirected graph.
Actually, if we go to the if we change these direction to the undirected, then what will happen? It will go in any direction, and it has multiple at C point we can see we have option E, G, and F, right? So we can go to that on that point. We can go to F also. So that's why to go in a alphabetical manner, we are arranging that it in a directed, not in a undirected.
But whatever your question is valid. Yeah, correct. I think for undirected also you can draw the DFS tree.
Yes, sir. That's why I asked.
Yeah, you can.
But
Will have multiple poles of this
It will
vertex.
be
Anything will be connected to anything. Anything will be connected to it.
correct.
Very
Correct.
direction,
But
right? It will be fully
yeah,
Didn't
we
get
will get
your
different
point,
edges.
Shukla. So what did
Okay. I will
he
explain. I
say?
will explain. If there is no direction,
Yeah.
what happens is you will get the same BFS tree without direction. DFS tree, sorry.
Right.
Okay. You just remove the directions. So that will be a DFS tree for this particular.
Does that mean we are automatically in the order, like in alphabetical or
Yeah,
whatever
you
the
just
order
remove
it
the
is?
direction. That's it.
Okay, then it is possible.
Yeah.
If there is no order, then we can't like say anything about that, right, sir?
What is if there is no order?
Like if it is not that alphabetical order or
Then
in
there
a
will
ascending
be
or a descending order.
then there will be so many number of DFS trees for one particular starting point.
Okay.
In order to compute itself, that will require a lot of computation.
Got it, sir.
It will be almost infeasible if you have very large number of nodes. Then it will be very computational.
Yeah. Okay, let's come back. Let's come back and see this. So this is the DFS tree of this particular graph. This is very much different from what BFS tree. So we have computed BFS tree for the same graph. It has only some 2 levels. Correct?
Yes.
So above we have computed. But see here,
yes, sir.
There is a long path going from A to G. So can I find the shortest path using BFS tree?
No, sir.
No, sir.
The
No, sir.
longest path. Only longest path.
So DFS doesn't necessarily find the shortest path to a node, sir.
Correct. So that is not an application of. What conclusions can I draw from BFS tree then? So why is this important? So BFS, I have given you some 2 conclusions.
Get the order.
Get the order. No.
Every node will be visited. Every vertices will be visited. Even BFS.
See, that is one conclusion we can draw, even if it is for BFS or DFS. So the reachability can be find out.
Yeah.
So you can
Find out
actually.
visibility.
So one conclusion is reachability can be find out from this DFS tree. So you can see all the vertices in this particular DFS tree. So that means from A you can reach every other vertex.
One thing I want to ask, sir. Like if you want to if you want to find an answer in not in the form of graph, in the form of like A, B, C, D, E, like in that format, then can we say it is A, B, C, E, D, G, and then F?
Yes.
Okay.
Correct. So that is how it is.
Got it.
Okay. Another conclusion is not the conclusion. One other application is you can find the cycles. So in BFS, if it is undirected only, you can find whether it has cycle or not. But you cannot find using BFS. If it is directed graph using BFS, you cannot find whether there is a cycle inside your graph or not. But DFS tree does that. So if there is a backward edge, so now I use the new term called backward edge.
Yes, sir. This thing also not able to get it from the video backward.
Right. So now that I have a DFS tree with me, so how many edges I have already used from the original graph? So A to B edge. So A to B is used. B to C is used.
N edges.
C to E. E to D.
Six.
L to E,
11.
and C to F. So I have used 6 edges, and I still have some edges.
4
which I
edges.
didn't use. So
Not 4, 5.
This edge.
5 there.
This
C,
edge,
G,
this edge,
F, G,
and
D,
this.
F. Right.
So there are 5 edges I didn't use. Using these edges, we can actually find whether there is a cycle or not. So how do we do that? So what we do is we actually bring those edges and try to draw it on the DFS tree. So there is an edge from A to E. So if I draw an edge from A to E, how that will be? So
A directed to E.
correct. So this is an edge.
A
And what are the
directed to
other
D.
4 edges? A to D.
A to D.
A to D.
C to G.
So A to D. C
B
to
to
G.
G.
C to, oh, sorry, B to F.
And B to F.
F to G.
And F to G.
Yeah.
So now you see, I can see some edges coming from A and going to downside of your DFS tree.
Yeah.
Okay, in the same direction. So from A to E, I also have a path from A to E and also have an edge from A to E. Okay.
Yeah. Yes, sir.
Understand this? So if
Yes, sir.
there is an edge coming from above level to below level, then those edges are called
It is a forward.
Forward edge.
they are called forward edges. Okay.
Got it.
And also I should mention one more thing called branch.
Sorry?
So then only you can differentiate between forward and cross edge. So in this particular tree, this particular path is called one branch.
F to C, right?
And this is another branch. There are 2 branches in this BFS tree. So you start from one vertex and you go to the last vertex you see. So consider all those vertices in that one path, and that particular path will be a branch, separate branch.
In one where we have six
Yeah.
vertices,
So
and
A,
in two
B, C, E,
D,
D,
G.
G. So this is branch 1.
6
And there is
vertices.
branch 2, which is A, B,
C,
C,
F. Right.
okay. So this
Yeah.
is one more branch. So likewise, in your DFS tree, you can have 4 or 5 or 6 branches, depending upon the last vertices. So there are
Got it.
2 last vertices. So there will be 2 branches. Okay. I will take
Sir,
one more
but
example.
what will be the
What will be the?
just forest? What will be the difference between branches and forest? Forest is also a terminology used, means multiple trees create a forest.
Multiple trees creates a forest. Okay.
Yes,
So within a
in
tree, there will be
DFS.
branches. So you
Yes.
understand, see that those terms are taken from the real meaning sense, real meaning only. So
Yeah.
you see the forest has many trees. In forest, you know
Yes.
forest, right? Forest will have many trees, and
Yes.
each of the tree will have some branches. Each tree
Yes.
has branches, right? So that is what, that is the same naming convention we use here. So each tree can have multiple branches, and if you collectively look at some 10 trees, 10 different trees, and that is called a forest. 10
Yeah.
or 100
Can we
or
say like that, like a bunch of
May I say-
branches is called
see this is
forest.
a tree with 2 branches. Okay.
Yeah.
Okay. Like this, I can have like this. See, this is one tree.
So basically, sir, a tree is a connected graph with no cycle.
Yeah.
And forest is a graph with each connected component a tree.
Component, yeah, correct.
Yes.
Right.
Yes.
So this is
component, then it will not form a tree. Means it will form a different tree. We have to find that unconnected vertex.
correct. So this is a forest with the 2 trees.
Yeah.
Okay. So this is one tree and this is another tree. Collectively is a forest where each of the component is a tree. There are 2 components in your graph, and each component is a tree and connected individual. So this is a disconnected graph. So there is a disconnection between these 2 graphs. Okay. So collectively is a forest. So you don't worry about forest. We are not going to deal with forest here. So you only need one tree, and within the tree, the number of branches you have. So once you understand the branches part, now you see within the branch, if there is an edge in the same direction, so that is called a forward edge. So I have an edge from A to E, from A to D, and I have B to F, so which is here, and another is F to G. Now these are the, I got only 4. What is the one more thing? C to G.
C to G.
Correct. Now see, these particular edges are on the same direction, or on the same direction of the branch direction. So let's consider this as the branch direction. So A to E also the edge which is in the same direction of the branch direction. So these edges are called forward edges. So AE is a forward edge, AD is a forward edge, CAG is a forward. Within the branch, if you have an edge which is not from the DFS tree, but you have an edge in the original graph, so that edge is actually within the branch, then those are called forward edges. And what is a backward edge?
A to B also.
From D to A, D to A, whatever it is, like
this
back.
particular graph is, I took it as a DAG, so I don't have a backward edge.
Going
Yes, there's no backward edge in this graph.
So if there is no backward edge, there is no cycle. I will take an example of it, but let's see what is cross edge now. So here there is a cross edge. So if there is an edge between two branches,
Where, sir?
So here you see F to G. So F is in one branch, G is in another branch, and there is an edge from F to G. So you
Sir,
see,
branches are always from first to last, sir.
Yeah, first to last.
First to last is a branch. In between, they are edges. Am I right? Right, sir?
So A will be in every branch.
Yeah, got it.
If you are starting from A is the starting for every branch. How many branches you have in that particular tree? Every branch will start from A.
Okay.
Okay.
Yes, sir. Got it.
So now you see there is an edge FG in my graph, original graph.
Yes.
And F is in one branch, branch 2. G is in another branch, branch 1. But in the original graph, there is an edge between F and G, which are F is in one branch and G is in another branch. So if there is an edge between two different branch vertices, that particular vertex is called a cross edge. Okay, this is not forward edge or backward.
Yes, cross edge.
If you can't figure it out whether it is forward or backward, that is a cross edge. Okay. So forward edge means within the same branch, you should have the same direction of the branch direction. That edge should have the same direction. So
in forward we have A to B also.
A to B is already an edge in the DFS tree. Okay.
Okay.
Okay. We only give names to forward. We only give names to the edges which are not in the DFS tree, but the edges which are in the original graph.
Okay.
Okay. So we don't give any name to. So any name to means these are edges in the DFS tree.
So these are tree edges.
Tree edges. So you can call it as a tree edges. DFS tree edges. These are tree edges. And these are forward edges, backward edges, and cross edges are the edges which are in the original graph, but not in the DFS graph, which are not in the DFS graph. Okay, I will take DFS graph, DFS big graph, and we will talk about cross edge and everything. So this is A, B, C, and D, and E, F, G, H, I. Okay. Now tell me how many branches are there in this particular graph? If this is a DFS tree.
Four branches.
4 branches. Correct.
4.
So you see the last vertices. There are D, E, G, I. So there are four last vertices. So there will be 4 branches which are. So this is branch 1. This is branch 2. This is branch 3. And finally, this is branch 4. Okay. So there will be 4 branches in this particular DFS tree. So now I will draw. So let's say in my original graph, I have few edges. Okay. Few more edges. Other than these 3 edges, I have some more edges. I will draw that edges now.
Excuse me, sir.
Yeah.
Thank you so much. So we have to leave now. We have Python's session will start.
You have Python session. How many of you have the Python session? I will end it. It's not like I can end it.
CT is also there.
CT is also there. Okay. You should tell me, right?
Python
If you sit
started.
silently, how would I know? Okay. Then we will continue in the next class maybe.
Okay.
Tomorrow.
Thank you so much.
Yeah. Thanks a lot. Thanks. See, you should inform on me, okay?
Yeah.
Nothing like
Yeah,
you
we will.
inform, I will take it in a wrong way.
Sir, you finish it off, sir. This point at least.
Finish it this point.
Yes, sir. This point you please finish.
Okay. I will conclude with forward, backward, and in this particular thing. If I have an edge between E and G, okay, in my original graph, if I have an edge between E and G, G is in one branch and E is in another branch, then this particular edge is called a cross edge. Okay.
Yes.
And if there is an edge which is going like this, going backward to the branch direction.
Backward edge.
So from C in your original graph, if there is an edge to A backward, like branch direction is like this, but it is backward to that. So these are called backward edges.
Yes.
Okay.
From lower level to higher, sir.
From lower level to higher level, if you have upper from the lower to
upper rather.
Upper level, if you have an edge in the original graph, then those are called as the backward edges. And those backward edges will create a cycle. How you know A to B, B to C, and C to A is a cycle. Okay, you start from A, you come to B, B to C, and C to A will create a cycle. So now
yes,
A,
now I get it.
B, C, and C to back, I have an edge, backward edge to A. So this is a cycle now. This will create a cycle. Okay. So you can actually find the number of, if there is at least one backward edge in your DFS tree, then your original graph has a cycle inside it. So that will not be a cyclic graph, that will be a cyclic graph. And if there is a direction and it is acyclic, that is called a directed acyclic graph, that we will discuss later. Okay, these are called backward edges, these are called cross edges, and forward edges are within the same branch. If you have a upper level to lower level edge in the original graph, these are called forward edges.
Sir, let's suppose if we has a vertex, sorry, a node edge from C to I, then it also will cross this. No?
This is also a cross edge. If there is an edge from C to I, this will be a cross edge.
Sir, can I leave, sir?
Yeah, please. Okay, I am
you,
done.
sir.
Okay, thanks.
Thank you so much, sir.
Yeah.
Thank you, sir.
Edge between B and F.
D and F.
Yeah. Is that a possibility like that? No, B and F. B for ball.
B and F.
This is a separate branch. So.
Oh, these are separate branches, right? B and F are two different separate branches. So this will be a cross edge.
Okay.
Okay. So this is how if you know the original graph, if you know the DFS tree, so just plot the non-tree edges which are in the original graph. Just plot the non-tree edges in this DFS tree and see whether it is backward, forward, or cross edge. Okay. Cross edge we will not infer anything. But for backward edge, we will infer something. That is, if there is a backward edge, then there will be a cycle. Okay.
Sir,
Hmm.
sir, so in DFS, like there is one question, whether age there should be any like B2F, there would be any age is possible or not. So in solution part, it has written like if the branch are different, then edges is not possible.
Yes.
Branch are different, edges are not possible.
Yeah, like if it was with number like 8 to 10, is there cannot like there was option. Yeah, right. So in solution part, the explanation was given like if branches are different, then there cannot be any edge.
I know that means if vertices are in the two different branches, then the edges are not.
Yes, yeah, vertices, if vertices are in different branches, then edges cannot be possible.
Actually, it is just a possibility. If there is a possibility that edges are not possible, so that is the question.
Yeah, so that is a possibility, right?
So like in BFS and DFS, there are, I mean to say in BFS, we only count the level one, like
Level,
if
yeah.
okay, that was like difference between these two. I was like confused.
So we had a prediction in BFS, no, like if the levels are greater than 1 and there is no possibility.
There is no possibility.
Likewise, we
For DFS also it's there. For DFS also it is there. Yeah, for DFS it is there because see, this is a directed graph, okay?
Okay.
Yeah.
So if this is a directed graph, then you can have cross edges between branches. Okay. But if it is an undirected graph, given to you, and if you draw the DFS tree, then you cannot have an edge between two different branches. Did you? Okay. I will give you an example.
No, we're not able to visualize that.
Yes, sir.
So see, let's say this is my graph. Okay, those who have class CT and everything, you can leave. Okay. Those who, so
I
hope
have
you
class, sir, but I cannot leave.
Okay. I will complete it quick. Okay, this is an undirected graph. Okay, let's start from A and perform the DFS.
Okay.
So A to B, B to C, C to F, correct? F to E, E to D, and there is nothing with D, and I have to come back to C, and C to G. Okay, now you see. Okay, not to G, not to C. So see, after D, I have to come back to E, and I have to come back to F. Once I come back to F, there is an edge. There is an vertex which is unexplored, which is from F.
Yes.
Okay. What we are doing actually, so you are starting from one vertex, and you are moving to the neighbor of that vertex, and after that vertex, you are moving to another neighbor of that vertex. Like this, you are moving, and once you reach a dead end, you just come to the previous junction, and you explore, and previous junction, and you explore. For suppose you say you have an edge between D and G. So if there is an edge between G and D, once you reach D, why you are going back to E? Because you know that after D, there are no vertices which are neighbor to D and to be explored. Correct? That is why you are going back to E.
Yes, sir.
Is she there or left or?
No, I'm there.
Yes, sir.
There, right?
I'm there. Yeah.
Okay. So my question is, so why we are going, once you reach D, why we are going back to E?
Because there's no
to check whether is there any unexplored thing.
when we will go back to E, if there are no unexplored vertex of which are neighbors to D, then only we go back to E.
Right.
Right?
Yeah.
So D is the dead end. Like dead end madlam, there are no unexplored vertex which are neighbors to D.
Yes.
Correct? So that is
Yes.
why we go back to E. So once
Yeah.
I go back to E and I'm going back to F, means what it means? There are no unexplored neighbors of E also.
Right.
So if I had an edge between E and G, let's suppose say if I in my original graph, if I had an edge between E and G, what should have happened?
Then we will go to G,
After E,
not
you
F.
should explore. Yeah, after E, you should
Yes.
explore G here. But instead, G is coming here. So that means you cannot have an edge between E and G.
Same thing for D and G also, no, sir?
Same thing for D and G also. If there is an edge between D and G in your original graph, so once you reach D, so you will look out for an edge, look out for a vertex which is unexplored. If there is an edge between D and G, then you will explore G here only. It will be in the same branch. So what it
Yes.
tells you is whatever the vertices in your DFS tree, if your vertices in the same branch, then you can have an edge between among themselves. But once it is in the other branch, that means there is no connection with this branch. So this particular vertex G doesn't have any connection with E and D. So that is why it went to different branch. If there is a connection with E and D, E or D, this G must have come here only.
Yeah, right.
Okay.
Got it, sir.
So that is why. So the conclusion is within the same branch you can have the edges. So in order to predict the graph, you can have an edges within the branch, but you cannot have edges outside of the different branches. You cannot have cross edges in an undirected graph, only in undirected graph. I'm specifically mentioning about undirected graph. Okay.
Okay, okay. So like this theory for like finding the edges, it's not applicable for BFS, no? BFS for only level checking.
BFS is level checking. So that is why you check when you wanted to find whether there is an edge between two vertices or not, or predicting the original graph. If it is BFS given to you, so you should be like one level above or one level below, there can be edges or in the
Got
same
it.
level. But in
Got it.
DFS, it will be like same branches. Same branches you can have edges, but different branches you cannot have edges. So this is the difference between BFS and DFS.
Okay, okay.
Yeah, okay. Okay then.
One last
Sir,
question. Can the undirected graph also have this backward connection?
There is nothing called backward in an undirected graph. So what is, see,
Okay.
direction only, there is something called forward and backward. So if there is no direction, nothing like forward and backward. So the same follows. So if you have any edge which is not non-tree edges, if you have one more edge, that will create a cycle if it is undirected. Okay.
Okay.
Sir, looking at particular branches also, if you look at this branches, right? So each branch forms a cycle, right? In this undirected graph.
Each branch forms a cycle.
You have the A, B, C, F, G.
A, B, C, F, G. Here it formed a cycle because there is an edge between A and G.
Okay.
Which is a non-tree edge, right? So that is what I said. If it is undirected, if you have at least one non-tree edge, whether it is A, G, or there is one more thing, GF is all GF, CF. So there is CF also, CF edge also, which is a non-tree edge. So these are non-tree edges.
Okay, right. If that exists, then that forms a cycle. Okay.
Then that forms a cycle. Whether it is BFS or DFS, if it is undirected, if you have one non-tree edge, that will create a cycle.
Okay. So there was one question in the active question for stack saying that they were asking whether the stack is whether last in first out or first in last out. Basically, both are same. Then why we are not considering first in last out for stack? No, I'm telling you
last out.
Yeah. Yeah, because stack works in that way.
So that is different algorithm, right? First in last out is different from last
No,
in first out.
First in first out. No, I'm from the words or last in first out is like
we take the last one and process first. First in, last out.
Basically, this is a step when you put CD one after and another. So first step is we have to remove the last one. That's why last in, first out. We cannot move the first in last. This is the possible, but then we have to empty whole stack. Then it's telling the first in, last out. But whenever collecting the CDs from the stack, we have to what CD we put last. We have to first pick up that CD.
No,
So
that's
last
right.
in, first out.
No, that's correct. That's what you said is correct. But looking at the first option, right? The first one will be processed only at the last.
First one will be processed at the last.
Yes.
So
this is to remember that thing LIFO and FIFO. That's why.
No, that's philo. We are talking about LIFO and philo. Even if you take the concept of stack, the first element which you put into stack will be processed only last. So from the
So what is this LIFO and philo?
These things, last in, first out, and first in,
Oh,
last
okay,
out. In short, we call it as FILO and LI.
Okay.
And there is first in, first out, FIFO.
Okay, got it.
See, how the algorithm is performing is what the statement says, okay? How the algorithm is performing, whichever comes the last, that will go out first. So that is how the algorithm works. Algorithm is working.
That's right.
That stacking thing. So this is coming first, I agree. And next it will come one thing and other thing. But the algorithm, how this algorithm is performing. So whichever, if you want to perform the algorithm, whichever came in the last. So
okay, you're talking about processing. How
after stacking, what is the process you are going to do?
Which one we put it last? We will be processing it first.
We will be dropping it first.
Right.
Correct?
Yeah.
Yeah, there is a debate. Even in the last batch, there is a long debate happened. Why not first in, last out also?
Excuse me, sir.
Yeah.
But the stepwise, if you're saying, then the first step is first we move the last thing. Then we can go on and go on.
Sir, can you please show an example to predict the original graphs from BFS or DFS tree?
That we did. That we did. Just you go back in the YouTube session, you will clearly understand. We did for BFS.
Yeah, I was in the session, sir.
Okay.
Just asking you to show an example, like with some trees.
Okay.
Here you just show the lines and no, sir. Here.
Okay, I will just show the lines only.
Yeah.
So one question before that, there are 16 people. Do you have any question, or are you still waiting for me to?
No, sir, we don't.
I will say something kind of nothing. So I'm not going to deal any new topics. That is what I want to convey. Okay. Okay, let me take it. Just give me 1 minute. Okay.
Okay, sir.
Okay. So you see, this is a BFS tree. Maybe one more thing. Okay, if this is a BFS tree.
Yes, sir.
We have concluded that either one level above or one level below or the same level can have edges. So if we give you, this is the BFS tree, if we say this is the BFS tree and predict the original graph.
Yes, sir.
Okay, you can predict by, so you can take the maximum edges. So in the same level, first connect the same level vertices. So you can have edge between B and E.
Yes, sir, we do.
D and F, F and G, like this. Also
Yes,
D
sir.
and G, C and F, like this. I can have